The tablet is being unresponsive. All right. Abandon that one. Bust out the other tablet, which hopefully is charged. Good enough. We'll use this one today. All right. So last time we finished talking about electron configurations, and today we're going to start talking about trends that we can observe on the periodic table. Um, there we go. Okay, great. Let's just test this. Is it working? Yes. Okay, good. So we're going to be talking today about Chapter 7, which is trends in the periodic table. So we're going to be looking at the periodic table and understanding that the way it is organized lends itself for us to be able to determine a few things about many different atoms, um, including their size, their metallic character, their ionization energies, all sorts of good stuff. And all of this, we're going to see trends on the periodic table, meaning that we're going to see that as we head towards certain regions or certain like sides of the periodic table, we're expecting things to increase or decrease. And thankfully, a lot of these are pretty solid trends. A few of them have a couple of exceptions, but by and large, the trends are pretty solid. So, history-wise, uh, periodic table was kind of developed in what 1886, maybe something like that, somewhere in the 1800s, by Mendeleev, who had arranged them by their kind of properties, and had predicted actually some properties of elements that hadn't been uh, discovered yet. And when they were discovered, they were actually quite close to what he did predict, which is pretty cool. So just the power of understanding this arrangement led to that. And so maybe, like two-thirds, three-quarters of the elements were discovered by then in the like late 1800s, and the rest came afterwards. Um, and so the way it's organized, thankfully for us, we've already kind of seen some of this, right? What do you know? This stylus is a little better for drawing the periodic table. We've already kind of seen some characteristics, right? We saw that, um, we had different blocks, including the hidden F block there, um, of the periodic table that kind of housed different types of electrons. And so this model of the quantum mechanical model using the probabilities and all that didn't come out till after the periodic table was developed. So it just so happens that this organization and predicting trends already kind of agreed with what the model would say. And so that's pretty cool, right? That the model that came after the table still works with the same table, even though the model is completely based on mathematics and physics and has nothing to do with the periodic table. It just so happens that they work really well together. So we're going to see that overall, we're going to see certain trends on this periodic table. And the first one we're going to look at is something called Z effective, which is our effective nuclear charge. And the effective nuclear charge is essentially kind of how much charge the the outermost electrons will experience. So it's kind of a relative thing here. So it's just kind of how much the nucleus attracts the outermost electrons. That's one way to phrase it. There's probably 15 different definitions, but this is kind of one that works for me. It's essentially, it takes into account kind of electron repulsion as well, but it's essentially, it can be approximated. This is an approximation. It is not an actual calculation. And this number is not something that we're terribly concerned about knowing an exact integer value for. We can kind of predict it, and in reality, we might see it's a little bit different, but that's okay. We're going to see that these two variables, let's use purple. This is the atomic number, and this is the number of core electrons. I don't quite remember if we made the distinction for core electrons last chapter or not, but that is anything not in the outermost shell. For example, if we take potassium, potassium is what? Argon 4s1. I need to check my periodic table. Yeah, argon. Okay. So yes, argon 4s1. Thankfully for us, the electron configuration, the noble gas one, tells us already we have one valence electron, and all of these are core electrons. And potassium has an atomic number of 19. We have one valence electron, which means the other 18 are core electrons. Oops. Here's Z, here's S. We're predicting the effective nuclear charge of potassium to be +1. In reality, it's probably a little bit higher, but that's okay. We don't need to worry about that. Notice that this number is also just the number of valence electrons, the number in the outermost shell. So for potassium, that's the shell 4. All the stuff in argon is all core electrons. We're going to see that with elements with d electrons. Let's say, how about we look at tin here? So tin is going to be what? 5p4. So if you look at tin, its noble gas above it is krypton. 5s2, 4d10, 5p, what did I say, 2? Yeah, 5p2, that's tin. All right, found the periodic table. Important to remember that the highest shell is these two. Only s and p orbitals count, because d is not part of the highest shell. It's in shell 4, which is going to be core electrons. So d electrons are always core. I want to remember that. So we can approximate this by doing tin's atomic number is 50. We're going to subtract krypton, and we're going to subtract the d electrons. So we do that. Krypton is 36. That's krypton minus 10, which is the 4d electrons. And we get 4. So it's, in fact, the effective nuclear charge is essentially approximately equal to the number of valence electrons. So tin has 4 valence electrons. All the electrons in the 5th shell for tin are valence electrons. And we're going to see that tin's effective nuclear charge is roughly 4. And so it's approximately number of valence electrons. Approximately. In reality, I could probably give you some numbers, but they're not uh, terribly exciting. Um, because we're going to see that the effective nuclear charge is actually slightly higher as we go down the periodic table, but we don't really need to worry about that too much. So